Welcome to Plutus IAS, and today we are covering Jahn-Teller distortion. Now, before covering Jahn-Teller distortion, most of us already know what does Jahn-Teller theorem means. So before we move forward, let's just explain it. The JTD theorem states any system which has asymmetric electronic configuration, which is having asymmetric electronic configuration in the octahedral geometry will undergo distortion in its degenerate degenerate orbitals, which will lower its symmetry and will lead to the change in the bond length of the molecule, which in this case we'll be calling it as decrease in the symmetry of the molecule. Okay, so what do we know about? We know that this is our d orbitals in an octahedral diagram splitting environment. We get a splitting pattern like this with 3 T2G set of orbitals and 2 EG set of orbitals. Now, these orbitals, if you see right here, these orbitals are your degenerate orbitals. Why degenerate? Because all these three orbitals are at the same energy level. Now, these d orbitals are made of dxy, dyz, and dzx type of orbitals. These orbitals, since they lie in between the axis, whatever the repulsion these orbitals feel will be much lesser. While the orbitals which are dx square y square and dz square, which lie along the axis, will suffer the max amount of repulsion. Now, so in case of JTT, whatever asymmetry in configuration, for example, these three are exactly half filled. As soon as I fill one more extra electron, now these orbitals are asymmetrically filled. In such case of scenario, we'll say that Jahn-Teller distortion will occur. Okay, since these orbitals already suffer the lesser amount of repulsion, the distortion that occur because of the asymmetry in the T2G orbitals are much lower in amount compared to the case of the EG cases. Okay, if you are filling electrons in the dz square y square or dz square asymmetrically, like this case or like these kinds of cases, now the max amount of GTD that will be found is in the case of the D9 cases of complex. The D9 complex. Now we have the complex like this where all the bond length are of exact same size. Now, when asymmetry occurs, there can be two different options that are available for a molecule, which will lower its symmetry. Please keep in mind when I say that the lowering in symmetry means in terms of bond length. So that means one option is the axial bond lengths can grow larger in size. The other option is the axial bond length grows smaller in size. Or we can simply mean that the equatorial bond lengths grow larger. This kinds of cases is called as the Z compression type of cases or the Zn type of cases. Well, these are called as Z elongation or Z out type of cases. So here today we'll be talking about the Z type of cases, and we are specifically referring to the examples of copper H2O whole 6 2 plus, which is a case of D9 molecule of Z elongation. So how does this occur? So in the splitted environment, initially the electrons are filled like this. Here, the filled electrons initially lie at the dx square y square orbital, while one electron exists in the dz square orbital. Now, Since these orbitals lie in the paired up environment, they have higher shielding. They have higher shielding. Now, when they have a higher shielding, what we can say that in this case, whatever the ligand that is trying to approach the d square z square orbitals for the purpose of bonding, because of high shielding, this ligand cannot approach it well. In such case of scenario, the ligand will preferentially attack the dz square orbital. Hence, because of shielding, because of shielding, what will happen? If the ligand are trying to approach this orbital, they will be higher in energy compared to the case of your dz square orbital. And when redistribution of energy takes place, they will be paired up and like this. Okay. While this has very less significance for us, so we will not talk about. So in this case, what we can see now, in this cases, because of higher repulsion that they were initially feeling, you will have a complex like this. Now, when the z square orbitals, after the redistribution of energy, when the electrons get paired, now they will have a higher amount of shielding effect and more repulsion. Now, since in these cases, the more number of ligands are present in the equatorial plane, these dz square orbitals have no option but to minimize their repulsion. Their bond length increases because of these four types of ligand. And that's why the D9 cases are the cases of Z out or Z elongation for JTD. So I hope this would have cleared how JTD occurs in the case of the D9 cases of complex and help you remembering about different types of cases. So in the coming class, we'll talk about the Zn type of cases and more such examples regarding that. In case of any doubts, the comment section is all yours. And if you want us to make any topics, any more videos that you want us to be covered for regarding a specific topic, you can add it to the comment section. And thank you for joining us.